Okay, so I want to talk about quantum. Yeah, the camera is on. I would like to talk about quantum systems, quantum mechanical systems. In fact, we just talked with Alex just before and wondered how many people could say what's a quantum system on Earth. You have 7 billion people. I think if you ask the question, there are not many more than 100,000 who could tell you something about quantum systems.
I'm not part of that 100,000.
Well, you'll be part of it. So my concern, what I would like to do is that we have maybe 0.01% who knows what are quantum systems, so the most basic particles of our world. And I would like to address to the people the other 99.9%.
You are very, I don't know what to say, the word ambitious. Ambitious.
And so I think the way to do it is not to talk about theory, because quantum, yeah, it's a theory, but it's also something very natural. It's a part of nature. And there was a theoretical physicist, Per Bach. He was a Danish physicist, and he was specialized in modeling dynamical systems. And out of his models, pictures, he could deduce power laws, mathematical power laws for his systems. And his opinion was that the ultimate understanding of scientific topics is measured in terms of our ability to generate metaphoric pictures of what's going on.
Could you please repeat this statement again?
Yeah, it's a quote. It's a quotation of his work. Our ultimate understanding of scientific topics is measured in terms of our ability to generate metaphoric pictures of what's going on.
Okay.
So when we have his I think his concern was about the sand or little systems that were interacting, and he developed pictures, metaphoric pictures, that helped him to show and to explain what was going on in those systems. And that's also my concern for quantum mechanics.
How nature works is...
Yeah, so he has written a book, How Nature Works. I have not written it, but that quote is from that book. So here's what they teach you at university. Quantum mechanics, and even sometimes they even don't teach it that way. Often they begin talking about quantum mechanics. They say, well, interference, it's okay. Schrödinger cat, weirdness, or entanglement, some stuff that you don't, that are very difficult to grasp. And we should, in fact, start at the basic principles. So the basic principles, they are taught in a theoretical way. So I took these postulates from a book. It's a book that was used by John Bell. John Bell, he was a famous quantum physicist. Quantum Mechanics Fundamentals, quote Gottfried. The first postulate is that the most complete possible description of the state of any physical system S, so any physical system, a table, a bed, or at any instant is provided by some particular vector, psi, etc., etc. I showed it yesterday to my son, and of course he was lost, or he I think when you present it this way, you put away there are 99% of world's population who won't understand what's a quantum system.
So it doesn't even depend on age.
And it doesn't. It's not because of his young age, but it's not. Well, you need some background before you can understand this. Like this, physically meaningful entities of classical mechanics, such as momentum, energy, position, and the like, are represented by Hermitian operators. Okay. You understand that only if you have done 2 years of
Or if
university.
you have Google aside and immediately search for Hermitian operators.
Well, and then most people can't read that article anyway.
Yeah. Third postulate, it's worse. Well, in that book there are only 3 postulates, but there are, in some books they present you 4, 5, 6 postulates. I think we could do it otherwise. We could talk just about the principles of quantum mechanics. And quantum mechanics, it's about the tiniest particles. So there are building blocks in nature, well, we call them photons or electrons, quarks. They behave all in a very natural way, in a quantum mechanical way. And to understand how they behave, we need to explore metaphoric pictures. So there are some possibilities in nature to do that. Well, we know about Couder's experiments, where you have bouncing droplets on a surface. That simulates, it's a metaphoric picture for quantum systems. I will take a slightly different way, but it will join, it will come at the same conclusion. It will come at the same conclusion. I will begin by the first principle. First principle of quantum systems is that they are represented by arrows. So an arrow, it's a very common object. I brought some objects like Mikado sticks. You could say it's an arrow. You can take a ball pen or even a baseball bat. I can say that this is an arrow. Twirling batons are arrows. We can look at the way such objects behave, and we will see that they are metaphoric pictures for quantum particles. So quantum systems are represented by arrows. I discovered this way of explaining quantum particles by Richard Feynman. Richard Feynman, you all know about him, a very famous physicist, and he gave a lecture where he also tried to explain how quantum particles were interacting, electrons with photons, and he said that he could explain the behavior or the measurements on quantum particles in a very simple manner. So he told, you will have to brace yourself for this, not because it's difficult to understand, but because it's absolutely ridiculous. The basics of quantum mechanics are ridiculous. If you think about those maybe 10,000 people on the world that understand some basics of quantum mechanics, or 100,000, versus the rest of the people who don't understand it, it's ridiculous, because they could understand it if they were taught about it in a simple manner. Just say to them that all we do is draw little arrows on a piece of paper. That's all. Okay? So draw arrows. Everybody, I think, knows how to draw arrows. I've tried to build some, or to give some arrows. This is a picture for a quantum system. Here we have some quantum particles. So what quantum physicists do is that they take particles, they say, well, we have an arrow or a needle or a baseball bat, and we say a particle has some properties. It has energy, it has a position, it has momentum, and we have the second particle which has energy, position and momentum, and the third particle. And we will describe it, and I'll describe it in a slightly different way, in a mathematical way, and I will say it's a vector. A vector is just an arrow, okay? So this is the arrow representing the quantum particle. And they have, some physicists use this notation, just a cat, bracket, and they put the properties of that particle inside the bracket.